Hello and welcome to MT3. This is I'm going to be taking you through an overview of the first part of our course, which is vector spaces and matrices. Now, in this part of the course, we will be using Riley, Hobson, and Bence, and will be almost entirely in Chapter 8 of Riley, Hobson, and Bence, which deals with matrices and vector spaces. Now, Chapter 8 contains more material than we will be covering, so hence this overview. I will show you the sections we are actually going to be using. We're going to begin with from the start, so 8.1, and here's where we abstract out what it means to be a vector. The line with the direction is one example, but you're going to see that many other kinds of objects can be treated as vectors because they satisfy an abstract definition of a vector space. So we begin with abstraction, and in fact, this is going to be the theme of this this treatment of vector spaces and matrices. You have encountered vectors before, encountered matrices before. Here we unify them and we extend them, generalize them. All right, then we have linear dependencies, and this is simply the idea that when is a group of a collection of vectors linearly dependent? When can you write one in terms of the others, and when can't you do that? This leads naturally to the idea of basis sets. Now, you all know that basis sets are rather special. There's a collection of vectors which can be used to represent any other vector in the space. You know that. Your I, j, and k basis vectors span any point in three-dimensional space. After basis sets, we then will get on to the inner product. So far, this is all in Riley, Hobson, and Bence 8.1. The inner product is going to be a generalization of your dot product. Why generalize it? Because now with a generalization, and once you understand what it means to define the inner product, you can extend it to any dimension. You can extend it to to curve space-time, to as you will in general relativity. But here we will focus on just Euclidean geometry, so we will have a simple definition of the inner product. Here we will encounter the Kronecker delta function. This is one of the many objects that can cause some confusion the first time you see it. It's quite simple once you've got it, but this is where we start getting a little bit more involved in the algebra, the index algebra. This is the kind of thing which you will see quite a lot when you do coding. When you're working with computer codes, you naturally work with arrays, with vectors, with multidimensional storage arrays, with indices, summing over indices, and so if you're a computer coder, this might be simple to you. If you learn how to do this computer coding, might some of the ideas there might become simpler. We'll end this particular part, so 8.1, on, it's quite a long section by the way, on with a few identities. The Schwarz inequality and the triangle inequality will be the two main ones, which you will not use much in MT3, but you will find them useful when you do certain topics in quantum mechanics. All right, now given the vectors, we would like to then start operating on them. This is going to be a very powerful idea. You have an object, you now operate on the object. So we'll introduce this idea of a linear operator. This is Riley, Hobson, and Bence 8.2. And linear operators, so the linear operator A operates on the vector x to give us another vector y. We will see that these operators might take you from one vector space into another vector space, or simply keep you in the same vector space. Now take an example. If you've got a space here, a two-dimensional space, here's your vector, you apply with the rotation operator on this, and this vector might get rotated into another vector with the same length, just a different direction. So you have seen these operators before. What we will see is that when you introduce a basis set, the operator A becomes a matrix. So matrices are going to be certain kinds of operators, a representation of a kind of operator which takes a vector x and transforms it into a vector y. We will then have a look at matrix algebra, determinants, and all these different properties of matrices, special kinds of matrices, Hermitian matrices, unitary matrices, orthogonal matrices. And this is all in Riley, Hobson, and Bence 8.3 all the way to 8.12. we will end this exposition with a rather lovely topic on functions of matrices. And then we move on to what is probably one of the most important parts of chapter 8. It's eigenvalues and eigenfunctions. This is Riley, Hobson and Bence 8.13 all the way to 8.16. And an eigenvalue problem is when you have a matrix A operating on a special vector x, which is going to be the eigenfunction of, or the eigenvector of A, and that operation gives us a constant lambda times x. This is the analogy of what you have seen in quantum mechanics already. The Hamiltonian operator, which is a differential operator, operates on the wave function, an eigenstate, and gives us an eigenenergy E times the eigenstate. And you can see that this is almost identical. This will lead to concepts like a similarity transform, which is related to a change of basis set, and diagonalization. Now there are many more topics after this, but we will not be getting into them. This is how much we'll be stopping at 8.16 in Riley, Hobson and Bence. Now what about can you read any other book? Well, you will find these topics discussed also in the book by Arfken, and in the other reference book which I've introduced this year, which is Essential Mathematics for Engineers and Scientists by Pence and Wickman. So please have a look at those. If you wanted topics clarified from Riley, Hobson and Bence, get into the habit of looking into these other texts, because they can be quite useful. All right, so that's the bits we are going to be doing on vector spaces and matrices. Now after this, I'm just going to show you what's going to come after this. We're going to generalize the idea of a vector space to include functions, which is in fact what you do when you work with linear operators in quantum mechanics. There you work in what's called a Hilbert space. We're going to see that functions can be thought of as vectors, but in a very special space, which are going to be called function spaces, and there are different kinds of function spaces. The operators in function space will be differential operators for the most part. So the Hamiltonian is one example of a differential operator. It operates on a function to give us another function, or if it's an eigenstate, then you get the same function back times in energy. This will then lead naturally to concepts like hermiticity of differential operators, Fourier expansion, then differential equations more generally, and then we'll go into a whole bunch of topics dedicated just to solving differential equations. All right, so that's it for the first part of MT3, and let's stop that video here.